Welcome to our exploration of linear transformations, where we will study vector coordinates, the matrix representation of linear transformations, and the concept of change of basis. Let U be a finite-dimensional vector space and let V be an ordered basis, i.e. the vectors of B have been enumerated in some well-defined way. Let U belongs to U. Then there exists a unique n-tuple of scalars in F such that U can be written as a linear combination of vectors in B. The n-tuple is called the coordinate of U relative to the ordered basis B. The n by 1 matrix is called coordinate matrix of U relative to the ordered basis B. Let's find the coordinates of a vector 2, 1, -6 relative to an ordered basis defined by the set B, U1, U2, U3. We have to find C1, C2, C3 such that following equation holds. Simplifying, we get the values of C1, C2, C3 and hence the coordinate of U relative to the ordered basis B and coordinate matrix of U relative to the ordered basis B. Let U be an n-dimensional vector space over the field F and V be an m-dimensional vector space over F. Let B and B' be ordered bases of U and V respectively, and T be a linear transformation from U to V. Then each T, Oj, can be expressed as a linear combination of vectors in B'. By finding scalars for each Oj, we can form the following matrix, which is known as the matrix of linear transformation with respect to bases B and B'. If B and B' are same, then we denote this matrix as TB. Consider an example of a linear operator on R2 defined by an equation 1. If the ordered basis is given by the following, then we have to find the matrix of the linear transformation TB. The image of the vector 1, 1 under T is the vector 2, 3. We can write this vector as a linear combination of vectors of B. Simplifying, we get the scalars C1 and C2 and hence the first column of the matrix TB. Next we find image of the vector -1, 0 under T and do a similar calculation and form the second column of the matrix TB. Finding TB becomes easy if B is a standard basis. Let us understand this with another example. Let T be the linear operator on R3 defined by the following, and B be the standard basis of R3, which consists of vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. From the definition of T, the image of 1, 0, 0 under T is 0, 1, 3, which can be expressed as a linear combination of the vectors of B, and thus we obtain the first column of matrix TB. Note that the coefficients are the same as the image. By performing a similar calculation, we determine TB. Let T be a linear transformation from an n-dimensional vector space U into an m-dimensional vector space V, and let B and B' be ordered bases for U and V respectively. Then the coordinate of T, U, relative to B' is related to the coordinate of U relative to B by the following equation. Next, we understand the change of basis. The change of basis is the process of converting the coordinates of a vector from one basis to another. Let U be an n-dimensional vector space over the field F, and let B and B' be two ordered bases of U. Then there is a unique invertible n by n matrix A with entries in F such that, for every U in U, the following equation holds. The matrix A is called the transition matrix from basis B to basis B'. To find the transition matrix, we have to express each vector of B' as linear combination of vectors of B and make the coefficient as first column of transition matrix. Let us understand the concept mentioned in 6 and 7 by the following example. Consider a vector space R2 and bases B and B'. We need to find the following. In the first part, we need to find the transition matrix from B to B'. For this, we write vectors of B' as a linear combination of vectors of B and make the scalars as the first column, and hence we obtain the transition matrix. In part 2 we will verify the result of section 7 for the vector 2, 3. The coordinate of V relative to B' is equal to inverse of a multiplied by coordinate V with respect to B. By the following direct calculation, we get the same result. In the third part we will verify the result of section 6 for the vector 2, 3. The image of the vector 1, 0 under T is 0, 1, which can be written as a linear combination of vectors of B'. Solving equations we get the first column and so on. Now using the formula mentioned in 6, we can find the coordinate of t, v, with respect to the basis b prime. Same can be verified by the following direct calculations.